Good evening, and welcome everybody. Thank you everybody for coming out tonight, and thanks very much to the Whanganui Science Forum for inviting me. I think I got the first email about this presentation some time ago now, and I was asked to come up with a, well, provocative, maybe eye-catching kind of title for my presentation. So here we go, and I found a suitably apocalyptic-looking image to go on the back of this title slide. This is actually a picture from a fire in Spain a couple of years ago. But lots of images like this floating around on the web these days, unfortunately. So I won't necessarily be talking about the end of civilization, but a little bit about the possibility of that happening. Alright, so I believe I've got about 40 minutes or so. We'll see how we go. Just move that a bit closer so I can press the buttons. And I think, can everyone hear me okay? Okay, good. I'll keep using the microphone, I think, and just press these buttons. Turn it up? Okay. How's that? Hey, okay. Good, right. So when I was first contacted, I was told about this article in the Guardian, this social scientist saying that essentially, yeah, we're all going to die. Well, I guess we all know that's going to happen one day, but this person saying that this is going to happen to humanity, we're all doomed. And this is the reality no one else will dare to mention. Well, is that right? Someone else who's been in the media a bit, who visited New Zealand a couple of years ago, is Guy McPherson from the US. He has a website called Nature Bats Last, very true, and his idea is that in 2016, when I heard him speak, we had 10 years left to live. All of humanity again was going to be wiped out in 10 years. And when I heard him speak on the Kapiti Coast where I live, there were quite a number of parents with young children at this presentation, and people got really agitated at the idea that their kids were not even going to be able to grow up. And I really didn't like that, because as you might guess, I don't think that we are all going to die within 8 years now, because this was 2 years ago. The sorts of ideas he was talking about and the feedbacks and tipping points, some of these are real things, but we are really not talking about everybody disappearing in the next 8 years. There was an article in the Otago Daily Times a wee while ago about the decline in insects, so not exactly climate change, but related, and talked about the impending 6th mass extinction, which could wipe out land-based life from the globe. And what intrigued me was that this article appeared in the Life and Style section. I mean, it is about life, I suppose, in between sport and entertainment. And this is something else that bothers me. You often find these kind of articles, stories, sort of buried in the news somewhere, on a sort of, treated a bit like a novelty, bit of entertainment. I was on the telly a couple of weeks ago talking about this latest prediction of warm conditions for the next few years. That was all very good. I spoke to the reporter, and then as I was getting up to leave the studio, they were saying, oh, the next person we're going to have on is this man in the UK who's designed a line of toilet paper that has Donald Trump's face printed on it. And I just thought, okay, yeah, so it was breakfast TV, so maybe it's all about light entertainment. But after decades of the science community talking about this stuff, that is a little bit concerning that it's mostly still treated as a bit of a, not a joke exactly, but as light entertainment. It doesn't get as much coverage, say, the All Blacks, for instance. But then in the science community itself, there is certainly a lot of concern, and there has been for a very long time. This article in The Guardian, the UK newspaper, talking about the West Antarctic ice sheet has already started its irreversible melting and collapse. And this was published 4 years ago, I think. There's a particular climate scientist or Antarctic scientist in the US who was mostly quoted in this article, and it's his opinion, based on some pretty good data, that it's too late to stop the melting of the West Antarctic, which would mean 5 or 6 metres of sea level rise. But again, there's still a lot of discussion, a lot of argument about whether that's actually happening or not, or whether we've got to that point yet. So I don't think anything has been decided yet. We're not. It's very hard, you know. We're watching this all evolving. We don't have another planet Earth to look at, and we've never seen this happen before, so we don't know for sure what the timing of all these things is going to be. So, is humanity going to go extinct? Well, I think I've given you the answer to that question already. No, and that's not just my opinion, it's the opinion of the vast majority of the science community. I mean, maybe if you want to talk millions of years then perhaps, but I mean this century, no. Is it the end of civilization? Well, that's a maybe. I mean, that it could be, if we don't get on top of this climate change problem. So let's talk about climate change, and you hear often that climate change is very complicated and you've got to have studied it for decades to really understand what's going on. And if you want to get into it, yes, that's true, but the absolute basics, you know, the broad outline is pretty straightforward. So all of the energy that we have in the climate system, the weather, the winds, etc., all come from the sun originally. So the sun provides all the energy to power the weather and the climate. And the key point here is that the sun does not heat the air directly. The air is basically transparent sunlight. So the sun, some of it gets reflected by clouds and so on, but other than that, it shines through the atmosphere, not warming the air, and it gets to the Earth's surface, and that's where the sunlight gets absorbed. So the ocean mostly, because the Earth is mostly covered in ocean, but the land surface as well absorbs the sunlight. So the Earth warms up. And so the Earth radiates energy just like the sun does, but it's at a different intensity and a different wavelength and so on. And it turns out the atmosphere is not transparent to infrared, to heat energy. So there are gases in the atmosphere that we these days call greenhouse gases, you know, carbon dioxide and water vapour and so on, that are very, very good at absorbing the heat that the Earth radiates, just the same as the heat that our bodies radiate. So as a consequence of that, the atmosphere warms up as well, and so it radiates heat in all directions, half of which ends up heading back down to the Earth's surface. So the Earth gets warmed both by the sun directly, but also by this blanket of gases, the atmosphere on the surface of the Earth. And it's very like having a blanket on a bed. You know, if you're in a bed in the winter at night, you've got a blanket over you, you're going to be warmer than you would be without the blanket, because some of the heat that your body radiates is intercepted by the blanket and trapped underneath. So under the blanket, you're warmer than you would be otherwise. And it's exactly the same. This gas in the atmosphere is like a blanket over the whole Earth. And so what's under the blanket, that's the surface of the Earth, is warmer than it would be otherwise. If you put a thicker blanket on your bed, you're going to be even warmer. You put a thicker blanket on the Earth, it's going to get warmer. So if you put more of these kinds of gases into the air, things warm up. If you take gases out, it cools down. That's the basic principle. So you've got two options. If you want to change the climate, you can do one of two things. Change the amount of sunlight falling on the Earth, the brightness of the sun, or the distribution of sunlight over the different latitudes on Earth. Or you can change the amount of greenhouse gas in the atmosphere. That's it. That accounts for the ice ages. It accounts for all of the climate history that we're aware of over hundreds of millions of years. So at the moment, and certainly over a good part of the last century, the amount of sunlight falling on the Earth hasn't really changed much. In fact, it's gone down a little bit in the recent past. Whereas the amount of greenhouse gas in the atmosphere has gone up a lot. And we know from the chemistry of the carbon and the carbon dioxide and so on that it has to be from fossil sources, so fossil fuels, and it has to be from burning, because the amount of oxygen is going down as the amount of carbon dioxide goes up. That's a sure sign of burning. So we know that the increase in greenhouse gases is from human activity. So just to look at those two things, here's how solar output the sun, brightness of the sun has changed over the last 140 years or so, and the red line is one of the estimates of global temperature over the same period. So you can see the temperature scales on the right hand side, the vertical scale, and time from 1880 to the present along the bottom. And temperatures have gone up something like 1 degree in that time. And the brightness of the sun, you can see the ups and downs of the sunspot cycle. And the scale, the vertical scale on the left hand side is the amount of energy coming from the sun in watts per square metre. So that's a flux of energy in a average square metre of the Earth's surface. And it's gone up to about 1361 in the middle of the 20th century, so the sun did get a little bit brighter in the first part of the 20th century, and then it's been roughly constant and has actually decreased a little bit in the last 20 years or so. So overall, over that whole period, the amount of energy coming from the sun has changed by a small fraction of 1%. Meanwhile, the amount of greenhouse gases in the atmosphere have gone up very rapidly in the last couple of 100 years. So this is a graph of the amount of carbon dioxide in the atmosphere, going back over the last 13,000 years or so. The green and the red parts come from ice cores in Antarctica. Conveniently, little bubbles of air get frozen into the ice as it forms and compresses on the ice sheet. So you can drill down into the ice and sort of go back in time. Then all you have to do is melt that ice and it releases the air, and you just measure the amount of carbon dioxide or whatever it is you're interested in. And it's quite straightforward. The blue part is the record of direct measurements from the Mauna Loa Observatory in Hawaii, which is the longest running direct observatory of greenhouse gases in the world. It started in the late 1950s. The reason, well, there's several reasons why I show it like this. Often you see this Keeling curve, so-called, after Chuck Keeling, who founded the observatory in Mauna Loa, and it looks like it's sort of, you can see it going up, but it doesn't look too dramatic. But on the time scale of the Earth, this is how it really looks. So the reason we talk about carbon dioxide so much is because it stays in the atmosphere so long. You know, we're talking 1,000 years or several thousand years for a good fraction of it. So a lot of the carbon dioxide that went up in the use of the first amounts of coal and the first steam engines during the beginning of the Industrial Revolution, most of that is still in the atmosphere. We're probably breathing in and out a little bit of it right now. So when you put this stuff into the air, it stays there for hundreds and hundreds of years. So it would be thousands of years before that spike would come down naturally. And the other way of thinking about it is that the Earth itself operates on these sorts of scales, that the deep ocean circulation takes about 1,000 years to go one circuit around the world, and the big ice sheets take thousands of years to melt or to freeze. So, you know, this is the kind of thing we're talking about here, and this is actually just even this is a pretty short time in the way the Earth operates. So in terms of climate processes, you know, this increase in carbon dioxide is an absolute spike. It's almost an overnight change. And we're getting on for nearly 50% more carbon dioxide in the air now than we had back in the so-called pre-industrial period before about 1750. So you've got to go back a long way to find an atmosphere like we've got today, this much carbon dioxide and methane and all the rest of it in the atmosphere. Certainly more than 13,000 years, more than the last several ice age cycles, so you've got to go back more than 2 million years. In fact, you can use geological records to work out it's something like 3 million years since we had an atmosphere as we have in this room today. So it's before the evolution of humanity, human species. So it's definitely, yeah, hello.
If I may ask a question, what may have been the cause of that spike 3 million years ago?
Well, if I could answer that at the end, it wasn't a spike, it was a gradual rise and then fall again. It took a couple of million years to happen. But that was, yeah, through natural, it was volcanism mostly. So over a very long time, volcanoes can pump enough out to raise the carbon dioxide levels. But yeah, that's a good question. The rate of rise, you know, mostly in a century is, you know, hundreds of times faster than you'd see from the normal geological processes on the Earth. So yeah, we're really in uncharted territory in terms of the composition of the atmosphere at the moment. So this is our thicker blanket on the Earth. So the Earth, you would expect, would be warming up. And that is exactly what we see. So this is one of the estimates of global mean surface temperature on the globe, and this is from the NASA group in the US. And what's going on here is, again, it's from 1880 to the present. The last bar on this graph is actually this year, just the average up to the end of last month, end of July. And the temperature scale, well, 0 is our best estimate of what the pre-industrial temperature was. The temperature records don't go back far enough globally to take you back to the 18th century. But prior to 1900, we can estimate temperatures for at least 20 or 30 years or so, and that's where the 0 line's been set. So you can see there's plenty of ups and downs. There's El Nino events, there's volcanoes, all the rest of it. But you can see there's a pretty clear upward trend. And the last 4 years, that's 2015, 16, 17, and very likely 18 this year, are the only ones that have been more than 1 degree above pre-industrial. So jumping forward a bit, the Paris Agreement, which was not hammered out in Paris 3 years ago and signed off in 2016, talks about the nations of the world working to keep warming well below 2 degrees above pre-industrial. So we're at about 1.1 or something at the moment. And the bottom end of the Paris Agreement talks about keeping the warming to no more than 1.5 degrees. So you can tell straight away that we're starting to, head towards the lower end of the Paris Agreement range. So that tells you that really we probably don't have an awful lot of time to slow this warming down. I'll talk about that a bit later. So that's what's happening with temperatures that we feel, air temperatures, and this is an average over the globe, and of course different places are warming at different rates, and some parts of the world have actually not warmed at all. But anyway, that's the air temperature story, but air temperatures are really just a tiny fraction of the story. They're really the tail of the dog, because the Earth is mostly covered with water, with oceans. You find that 93% roughly of the total extra heating coming out of the atmosphere warming the Earth has gone into the oceans. So about 2% of the warming has been responsible for this degree or so of warming in the air that we've seen so far, and another 2% for the melting of the ice and the warming of the land surface and so on. But over 90% of the warming, extra heat has gone into the ocean. And the numbers are gigantic, a huge amount of heat's been soaked up by the oceans, which is great for us because it slows down the rate of warming of the atmosphere. It's been worked out that if all of this energy went straight into the atmosphere and warmed just the air temperatures would have gone up more than 50 degrees already, and we would all be dead, so we wouldn't be talking about this today. We would have all moved on, passed on. So it's fantastic for us that this ocean, this big sink of heat in the climate system, is doing its job. The only catch is that the oceans take a very long time to adjust. So we've already locked in hundreds of years of sea level rise, which might be quite slow if we get on top of the emissions soon. But the oceans are going to continue to change and adjust for at least several centuries from here. And I'll explain a bit later that having warmer water around Antarctica is not good news in terms of this business of the Antarctic ice sheets sort of starting to melt irreversibly. So there's a few issues with having lots more energy in the ocean, that's for sure. But one of the simplest consequences of warming the ocean is that, like anything, when you warm water, it expands. So as you warm the ocean, the column of water gets deeper. And that's one of the main reasons why we have sea level rise. So this is yet another graph, time along the bottom from 1880 again. And the vertical scale here is change in global mean sea level, GEMSL, in millimetres. And the 0 point was taken as 1880. So the blue line and the uncertainty shading there is the estimates from tide gauges from ports all around the world. And we have enough of these to make a reasonably good estimate of global sea levels going right back, going actually earlier than 1880. And then the red line is from satellite altimeters, GPS basically, which can tell in to great precision how far away the sea surface is from where the satellite is. So we have very good measurements over the whole of the global oceans for the last 20 years or so. And they marry up with the tide gauges pretty well in that period. So we've had about 24, getting on for 25 centimetres of sea level rise globally in that 140 odd years. But again, it's not uniform everywhere. Some places the sea level hasn't changed that much, other places the sea level's gone up much more than this. So there we go. And prior to 1880, you know, the beginning of the Industrial Revolution has taken us the middle of the 1700s. There was sea level rise before that, but it's I don't know if you can make out, this is not a straight line, it's a curve. So the slope of this line was about 1 millimetre per year back in the first part of the graph, about 2 millimetres per year in the middle, sort of mid-20th century. And since the turn of this century, it's been a bit over 3 millimetres per year. So the rate of rise is increasing. And that's because not only is the water expanding because it's warmer, we've also got ice melting and that water's flowing into the oceans and making the column of water deeper. And if you zoom in on the last 25 years or so and look in more detail, you can see the slope there, linear fit, the straight line, that's 3.1 millimetres per year since the early 90s. So that's about 3 times the rate of rise from 100 years earlier. And you can see at the last 7 or 8 years, the line looks a bit steeper, but that's probably just a bit of noise, a couple of El Nino events at the wrong time kind of thing. But the expectation is that the slope of that line will continue to rise as the ice especially starts to melt a bit faster. Glaciers around the world are monitored by the World Glacier Monitoring Service in Switzerland, and they don't keep an eye on every glacier in the world, there's quite a lot of them, but they do look at about 500 and something glaciers regularly, and they estimate the total amount of ice in these glaciers and how that's changing over time, and they imagine it's all melted into water and how deep would that be and so on. So the units are a bit strange, but I think the message is pretty clear that since this record started in 1980, on average around the globe, glaciers have been losing mass, losing ice. And you can see the slope steepen about the turn of this century, so the rate of loss of ice has increased in the last 20 years or so. And glacier melt, you know, that water does add to sea level, but that's not the really big issue with glaciers. And if you melted all the glaciers in the world and put all that water into the sea, you'd get about 0.5 metre of sea level rise. So you might say that's maybe not such a big deal. Well, that is a big deal, but the main problem with glacier melt and disappearance of glaciers is that a lot of populations around the world, especially in Asia and South America, depend on regular melting of glacier water for their water supplies. So I'm aware of communities, certainly in Argentina, that are already having to move because some of the glaciers in the Andes have disappeared, so their water supply has dried up. Then the ice sheets, the big ice sheets have been pretty slow to get going, but they are starting to melt reasonably quickly now, especially in Greenland. So this is a slightly old graphic from 2012. So there's 3 lines, again we've got time along the bottom, starting in 1992, because the good estimates of glacier mass only really came about in the last 25 years when we've got enough good satellite measurements. And the vertical scale is the loss, on the left-hand side is the loss of mass in gigatons, so 1,000 gigatons, 1 trillion tonnes of ice. And on the right-hand side, the contribution to sea level in millimetres. And there's this convenient exchange rate you can use. You melt 360 billion tonnes of ice, spread it out over the surface of the ocean, which happens to be 360 million square kilometres, and you get a layer that's 1 millimetre thick. So all you have to do is melt 360 gigatons of ice and you get 1 millimetre of sea level rise. And in this time, in the last 25 years or so in that graph, the sort of bluey line, the aqua line is Greenland, and that's been melting at a fairly rapid rate. The purple line, Antarctica, started later and has been slower. It's starting to increase its melt now, but it's contributed less to sea level so far than Greenland has. And the total contribution in that period was about 11 millimetres, so about getting on for 4 trillion tonnes of ice. So that was up to 2011. And if we melted all of the ice in Greenland and Antarctica, you could raise sea levels by over 70 metres. So about 6 metres from Greenland, about, not sure if it was exactly 6 metres, but something like that from the West Antarctic, and then about 60 from the East Antarctic. So the East Antarctic ice sheet's the really big one. And all of those are at risk in the next, or in the rest of this century. I'm not saying it would take a very long time to melt all of the ice in Antarctica. We're talking thousands of years again. But potentially we could lock in melting of a fair bit of this in the next 50 years or so. And here's an update of some of the ice melt statistics. So this is going through to last year. Antarctica on the left in the same vertical scale and billions of tonnes of ice. And you can see that Antarctica is melting faster now. I'm not sure if you can see, but it has melted at a faster rate in the last 6 or 7 years than it did in the previous 20 years. And the Greenland ice is still dissipating at a much greater rate than Antarctica is, but given enough time, Antarctica would catch up. Alright, so that's where we're at. And I guess the topic of this talk really is, you know, what's going to happen in the future. What about the end of civilization? So here's a summary slide from the last report of the Intergovernmental Panel on Climate Change about what might happen with global temperatures in the future. So the time along the bottom again, 1950 on the left-hand side and the end of this century on the right. Temperature change up the vertical. And the black line is what's happened in the past, up to 2005. We had about a bit over half a degree of warming in that time, and the 0 point is the temperature at the end of the 20th century. So if we do the Paris Agreement and we only get 1 more degree of warming, you're on that blue curve, roughly speaking, and the warming stops by about the middle of this century. If we do nothing, which is pretty much what's happening at the moment, you're on the red line, or maybe a little bit below it, depending on what's going on, and you're looking at maybe another 4 degrees of warming this century. So we already have 1. We might be up to 5 degrees by the end of the century if we don't take any action at all. So, the message here is we have an awful lot of power over the future. Yes, a lot more stuff's in the air, there's a lot more greenhouse gas in the air and so on. But if we take the right sort of action in the next decade or two, then we could make the future look a lot more like the present. If we carry on the red line, you know, that one keeps going up, and that's the one where you melt all the ice in Antarctica and all the rest of it. That would be a very unmanageable climate, I think. So I would say, you know, civilization is not about to go extinct, and if we take the right sort of action, you know, we can actually cap the problem within the next 50 years or so, and in my opinion that would be a very good thing to do. So, what about it? Well, what about, you know, we talk about a degree of warming so far, another degree this century. These numbers sound pretty small, really. I think we've seen some extreme events in the last year or two that suggest that even a degree of warming makes a big difference to some of the unusual kinds of weather we can get. But let's have a look at that. Let's imagine we've got this first 120 odd years, that time series of the temperatures that I showed before from the NASA group, but I've compressed it into the left-hand half of the graph here. And let's imagine, so we've got 1880 on the left, 2120, 100 years from about now on the right. Let's imagine that we do the Paris Agreement on the top end, we keep the warming to no more than 2 degrees above pre-industrial, and we get the same sorts of ups and downs as we've had in the past. Then if I came back and gave this talk in 2118, the graph might look like this. So you can see that's the 2 degree thing, the little tick mark on the right hand up near the top. Some of the years, beginning of next century, are just going a little bit above that, some of them a little bit below. The average is about 2 degrees above pre-industrial. And we've got similar ups and downs to what we've seen in the past. Now, 2016 is presently the warmest year on record, big El Nino event, and that's about there. So what this is saying is, you know, we're talking about 1 more degree in the next 100 years, so something like 1/10 of a degree every 10 years. then you see that there are some years in the future that are below that black line. But after about 2040, every year, so every year in the record is warmer than the warmest year on record. So what we presently call the warmest year ever seen, every year would surpass that by about the middle of this century. And by later in the century, the warmest year on record will be an incredibly cold year. So even a few tenths of a degree of warming translate to a totally unknown climate by the middle of this century. All of those ups and downs will be something that's never been observed before. So you get all sorts of crazy effects, essentially. So here's the results of a paper published in Australia last year that was picked up by the media for obvious reasons. And the researchers at CSIRO and so on are saying that you would expect to see temperatures above 50 degrees in Sydney and Melbourne before the end of the century. And I'm not saying that Whanganui is going to have temperatures above 50 degrees by the end of the century, but it's that idea that you would see temperatures beyond what's been observed before. I mean, I know Melbourne's had temperatures up to the mid-40s and maybe even high 40s once or twice, but never 50 degrees. And that's the thing, that you would start to see these records broken. And we've heard of records being broken in the Northern Hemisphere this summer with the intensity of fires and there's droughts and all the rest of it. So that's the kind of thing that could happen with an extreme, you know, you've got a hot day, it's that much hotter again kind of thing. And this would have all sorts of consequences for public health and infrastructure and transport and you name it. So what about here? So if you're looking at a 2-degree warming compared to a past climate, that would translate to something like a tripling of the number of hot days per year. And these numbers come from a report the Royal Society put out a couple of years ago. So if your threshold for a hot day is 30 degrees, and presently you get maybe 20 of those in the summer, you'd expect to get roughly 60 in the summer after a 2-degree warming, you know, by the end of the century kind of thing. And the places in New Zealand that are already on the dry side, like the east coast of both islands, are expected to get a bit drier. So it's warmer, so moisture evaporates more quickly, and you're getting less rain overall. So you would expect to see something like a tripling of the occurrence of droughts. And that translates to a big increase in the amount of time spent in either very high or extreme fire danger for a lot of the eastern part of the country. There are already places in Canterbury and the east coast of the North Island that do see 4 months or more of either very high or extreme fire danger. But that region, those spots where you see this at present, would spread out basically to the whole of the eastern part of the country, from south of Dunedin right through to East Cape and round into a little bit of the Bay of Plenty maybe. So that doesn't mean there would be lots more fires, but there would be the potential for lots of more events like this. This is a picture of the Port Hills fire near Christchurch the summer before last. And the big glaciers in the Southern Alps, the glaciologists at Victoria who model these things tell me that with this kind of warming and the changes in precipitation, you would expect to see the Franz and the Fox and so on recede up the valleys, and there would still be ice up near the tops, but there wouldn't be any tourism. You wouldn't be able to see any ice from down at sea level down at the road. So these big iconic glaciers would essentially disappear. And I've talked about how some places are getting drier and the increased frequency of droughts. Well, the perverse thing about climate change is that the amount of moisture in the air, the amount of water vapour, which is a greenhouse gas itself, is related to temperature. The warmer the air, the more moisture. So when it's wet, when you get a rainfall event, you get more rain. So extreme heavy rains and floods become more frequent as well. And this is again a bit of a broad brush statement, but you would expect a doubling or a tripling of the occurrence of major floods around the country by the end of the century with that kind of warming. And there's this little motto that came out of the last report of the Intergovernmental Panel on Climate Change. It doesn't work everywhere all the time, but it's not a bad thing to remember, that when it's wet, it's wetter, and when it's dry, it's drier. And that's really a consequence of it being warmer. Warmer, so when it's sunny, more evaporation, the soil dries out faster, etc. And when there's a storm, there's more moisture in the air to start with, so when it rains, you get more rain out. So you've got to worry about both ends of the scale there. Okay, so getting back to sea level rise, as the sea level rises, you expect to see more events like this. This is not around here, this is a road in South Canterbury about 3 years ago. There was a storm, the waves came inland and part of this road got washed away. And the reason I show this picture is these low cliffs the road's sitting on are probably, I haven't gone to measure them, but they're something like 6 or 7 metres high. So the road was 6 or 7 metres above sea level. But that's, that doesn't protect you. That doesn't tell you whether you are going to get washed away or not. The road was very close to the high tide mark, and the beaches are relatively flat things. So if you raise the sea level half a metre, the high tide mark comes inland by maybe 20 or 30 metres. And if you're that close to the high tide mark now, whatever it is, whatever you're on, unless it's an extremely strong structure or a cliff face, it's probably going to get washed away. So it's the distance from the coast, from the high tide mark, that's the issue. As the sea level rises, the waves, when there's a storm, can come inland that much more easily, and you do expect to see these kinds of events quite a lot more often. This is an image from just outside Nelson last summer. There were several ex-tropical cyclones that passed over the country. This is Cyclone Fahey, or ex-Cyclone Fahey, that was pretty fast moving. It only whizzed over New Zealand in 12 hours or so, but very strong winds. And again, the waves were washed over the road dramatically, and that has been made that much more easy because there's been about 20 centimetres of sea level rise in the last century around New Zealand. And I hardly need to make my point. Again, this is not whanganui, but there's some very expensive real estate in places like Auckland that are within a metre or so of sea level. So as you raise the sea level, this is just the general inundation, and I think the really worrying place is not Tamaki Drive, it's more like South Dunedin, which is already in trouble. And it's not just sea level rise, it's the fact that as you raise sea levels, there's there's a response in the groundwater, and the level of the groundwater rises too. So when it rains, it's harder for the rainwater to run away, so you get ponding and you get surface flooding. And last time this happened in South Dunedin, they had to bring in the fire service to pump the water out because it just wouldn't drain away. So yeah, you can get into a lot of trouble pretty quickly with a little bit of sea level rise. So with 30 centimetres of sea level rise, wherever you are, what you'd call a 1 in 100 year coastal inundation event would become roughly the 1 in 1 year event. And 30 centimetres more sea level rise is guaranteed basically whatever we do because of the slow response of the oceans. With a metre of sea level rise, then the 1 in 100 year event is now the average. Basically it happens every day, every tide. And that's if you're on the red line and you allow the emissions to keep going up. That would be the middle of the range now for sea level rise for the end of the century. And yeah, and a lot of us live near the coast, including me. It's a big issue, not only in terms of the cost of infrastructure, roads and houses and public buildings and power lines and sewers and you name it, but I love the ocean. I think a lot of us do here in Whanganui, we're all near the sea. And the coast has stayed in much the same place for nearly 10,000 years. Coming out of the last ice age, sea levels rose about 120 metres over 10,000 years or so. And since about, 8,000 or 9,000 years ago, sea levels around the world have pretty much been static. So modern civilization has got very used to living by the coast and knowing where the coastline is, and yes, the tide goes up and down and there are storms, but the average sea level hasn't changed for thousands of years. So we have all these big cities right by the coast, like Shanghai and London and New York and so on. And, the sea level is rising again, and we have to deal with that, we have to respond to that. And just getting back to this Antarctic business and the possible issues with irreversible melting of the West Antarctic and all the rest of it. There's been some modelling work done recently, the last couple of years, some at Victoria University. This group in the US produced a nicer graph in their figure, so I've used this one. So what's going on here is you've got time along the bottom again, going right out to 2500 now. And the vertical scale is the contribution to global sea levels just from Antarctica. So the black line is the sort of most stringent version of the Paris Agreement, where we only have 1.5 degrees of warming, maybe a little bit more, certainly less than 2 degrees. And you get, it's not quite flat, you get 20 centimetres or something out of Antarctica. But as soon as you go much over 2 degrees of warming, sometime in the second half of the century, according to the models, this is just a model result, but it gels with some of the geological evidence we've got of much higher sea levels at some times in the past where the atmosphere looked like it does now, such as that time 3 or 4 million years ago, sea levels were something like 10 metres higher than present. Sometime in the second half of the century, the warmer water that nibbles around the base of the ice shelves in Antarctica gets in over the shelf, over the grounding line, and a lot of Antarctica has been pushed down. It's actually below sea level, so the water flows down a slide with gravity under the ice and starts to lubricate it, and you get this runaway process where the ice starts to melt irreversibly. And it looks as though that would happen sometime in the next 50 years or so. And of course on the red line, which is the do nothing at all scenario, similar timing, but the amount of sea level is much, much higher. So within, we're talking 500 years here, but it could be 5 or 6 metres, or it could be 12 or 13 metres from Antarctica. And if that happened, you would expect to see another 5 or 6 metres from Greenland as well. So you can get up to 20 metres fairly quickly, although it takes 500 or 600 years to happen. But we could be locking that in before the end of the century. We could be changing the map of the world for 10,000 years within the next 50 years or so, maybe. All right. Not a lot of laughs in this talk, are there? What's the worst that could happen? What's the worst case scenario? This is sort of just about finished. And there was a very interesting article published in the New York magazine a bit over a year ago now by this journalist, David Wallace Wells. And it created a storm of protest, mostly from the climate science community, when it came out, because he'd taken the sort of upper end of all the projections in the IPCC reports and so on, and painted this picture of large parts of the Earth literally being uninhabitable, and hundreds of millions of people displaced or starving to death or whatever, really semi-apocalyptic stuff. And he got a lot of flack because it's this idea that you don't want to frighten people. I'm not quite sure why you came along tonight to hear about the end of civilization, but the theory goes that you don't want to frighten people because then they'll turn off and they won't take the right sort of action and so on. Anyway, I don't subscribe to that theory. And as a result of all this pushback he got, he produced, and you won't want to take down the address, but if you just do a Google uninhabitable Earth, you'll find it. He produced an annotated version of his article where there were links to all the people he talked to, all the papers he read and so on, and it's all backed up, It's all possible. It's not necessarily definitely what's going to happen, but there's some pretty scary futures out there. And his theory goes, his idea is that the public really don't appreciate the scale of the risk that we're facing. And that it's not so much that fatalism or people just turning off isn't the problem. Mostly it's complacency, that most people don't really think about it, they've got their own lives to lead, etc. And they just aren't too worried. And I would tend to agree with that many people are just not scared enough rather than too scared. So, interesting article, I'd urge you to have a look at it, and like I said, I'm not saying it's all going to come true, but it's sobering, it's food for thought, certainly. And we're talking about things like I was saying about these extreme temperatures becoming, sort of unknown extremes. And this is a map from a paper colleagues of mine at Victoria were involved in a few months ago, looking at, well, how quickly do high temperature extremes go out of the range that's ever been observed before. And the darker the colour, the quicker that happens. So in the tropics, and a lot of the tropics, we're talking within 20 years from now, we're getting extreme temperatures that have never been observed before. Down near the Antarctic coast, we're talking it might be another 150 years before that happens. But there are places not too far from New Zealand, and in fact, New Zealand itself, parts of New Zealand we're talking about, certainly before the end of the century, seeing extreme temperatures that have never been seen before in the historical record that we have.
Is that locked in with their present levels of CO2?
Oh, that's assuming, yeah, this is using one of the scenarios, not the most extreme one, but not the most benign, sort of one of the middle of the range guys. So yeah, it does depend on the total amount of warming. But all of these scenarios sort of overlap each other for the first 20 or 30 years. It's only as you go later in the century that everything sort of diverges. So I think some of these extreme exceedances in the tropics are virtually locked in regardless. But the longer term ones, yeah, would depend on us not taking a heck of a lot of action. And extreme temperatures and drought and so on inevitably impact on food production. So I think this is one of the big worries that, you know, global food production, global food supplies are on a bit of a knife edge anyway, and there's a lot of people around and there's going to be more people in the future. So the risk, I think, of food shortages and famine is definitely there for a lot of parts of the world. And then you have too much water. This is a photograph taken in Bangladesh last year. It was reported that nearly half the country was underwater. It's pretty hard to imagine, but it's a pretty low-lying country. So again, big floods in South India saw this record monsoon rains just a couple of weeks ago. Loss of life, huge damage to infrastructure, damage to food production, etc. going on as well. And ultimately, people get upset when they don't have access to water or food or the basic necessities of life, and this burning tank in Syria has been used as a bit of an example. That there's been quite a lot of work done suggesting that the big drought that occurred in the eastern Mediterranean prior to the Syrian civil war breaking out was one of the main precursors. So not saying that wars are going to break out everywhere, but climate change makes everything a bit harder and puts people on edge, and if you're already in a place that's a bit edgy to start with, the chances are, this kind of thing could happen. So the Pentagon calls climate change a threat multiplier. I think that's a really good term. If you're having problems already, climate change is probably not going to be your friend. It'll make whatever you've got harder. So there's going to be all sorts of implications, there already are implications for things like food security and regional conflict. Migration, what's going to happen? How are we going to deal with lots and lots of people wanting to come to New Zealand? Because New Zealand is one of the places that's the most sort of benign climate in the world, and so one of the places that will be the last to be really unpleasant to live in. Lots of people might want to come here, whether we want them to come here or not. So how do we deal with that? How are people going to travel around in the future? What's going to happen to air travel with the implications with emissions and all the rest of it? Who knows? And that's going to have some sort of knock-on effect to international trade. And if the country you trade with is in the middle of some kind of civil war or meltdown of some description, that's going to do something to the global economy for sure. All right, so just to wrap up then, what do we do about all this? So we want to stop the warming, stop the climate change. We've got this is what's going on. We've got this huge spike in greenhouse gases, especially carbon dioxide. We've got to turn that around. And there are people working on technologies to pull this stuff out of the air, but we're still waiting on that. So basically we need to stop making this worse. That'll be the first step. So we need to get onto this blue line. Start to reduce the emissions of greenhouse gases, preferably right now. 30 years ago would have been very nice. And the thing with the carbon dioxide especially, because it stays in the air so long, there's just a certain amount you can put up there to get a certain amount of warming. This much gets you 1 degree of warming, because we've already seen that happen. And you can do a pretty straightforward calculation to say, well, how much more have we got before we get 1.5 degrees or before we get 2 degrees? So you can do the budget calculation, basically. And the way it works out, at the present rate of emissions, we would lock in 2 degrees of warming within about, or no more than 20 years, so the late 2030s, isn't it? Yeah, 2038. But again, if we start reducing emissions tomorrow, we start pushing out that time frame. So if we do nothing, that's the story. And if you want to do...
That's bullshit. I'm sorry. That's bullshit.
Yeah, I'm afraid I'd love for it to be bullshit, but actually, sadly enough, it's not. And if you want to get 1.5 degrees, we're already well over 1 degree or over 1 degree. We're talking somewhere between 5 and 10 years at the current rate of emissions. before there's enough of this stuff in the air to get 1.5 degrees. It will take a bit longer than that to actually materialise, but we could be there before the end of the next decade. But again, if we reduce emissions, we went to half the emissions we've got now globally within the next 5 or 10 years. You know, we're talking 10 or 20 years, and then 20 or 40 years. So this is it's a pretty urgent problem, but if we get onto it, we can still get onto that blue curve. And we can do things like, I guess this is pretty well known, and the present government are right behind a lot of these things. Make our electricity system completely renewable, have more electric transport that, incentivise electric vehicles, use more trains for freight rather than trucks, a lot of electric public transport and so on. Make sure that any new industrial plant is powered by renewable sources rather than fossil fuels. Throw this stuff away. New Zealanders are really good at throwing away waste. In fact, we're about twice as good as your typical OECD citizen. So if we cut down our waste to the OECD average, there'll be less stuff in the landfills, less decomposition, less release of methane and so on. We could do interesting things with agricultural production, and I prefer the top picture here. We put balloons on all the cows and they fly away to South America. These are actually experiments measuring the amount of methane these ruminant animals produce, but it's quite a nice idea, I'd have to say. But even with present technologies around feed and maybe reducing stocking numbers in some parts of the country, you could actually reduce agricultural emissions quite significantly. And then you can plant a lot of trees, and this is another government policy, that trees as they grow suck up carbon dioxide, so that at least moves the time frame out of it, buys you a bit of time, if everybody did that. So New Zealand could reduce their actual emissions by about 40% within the next, 15 years or so. This was based on 2015 calculations. So there's plenty of, we know what to do really. We could reduce our emissions by nearly half by the end of the next decade, and we could at least help other countries to do the same. So, a lot of this is well known. We sort of know what we need to do. Alright, so, how much warming do we get this century? That really depends on us. I would say 1.5 degrees of warming is pretty much guaranteed already, unless something really dramatic happens. 2 degrees of warming, we hopefully could stop there. 3 degrees, who knows? But even 1 degree of warming gives you this big increase in extremes. You start to see these events that really haven't been observed before. And there is a certain amount of change already locked in, especially with sea level rise and changes in the oceans. So we're looking at more risk around sea level rise at the coast, increased frequency of droughts and floods and heat. Less frosts, that's one thing, but that's not necessarily good news if you have a crop that needs to be cold in the winter before it flowers and produces fruit in the summer. And we're just not used to this kind of thing. Like I said, sea levels haven't risen for nearly 10,000 years, and the global climate hasn't really changed for nearly 10,000 years too. Yes, there's been regional warming and cooling here and there, but overall, there hasn't really been a wholesale change in the climate for a long time, and we've all got used to that. But that's not the situation today. Everything is changing, and we can't use what happened in the past as any sort of guide to the future. So we need to think about this. We need to talk about it, and we have to be adapting to what's happened already. And my understanding from, again, it's not really my area, but the most resilient communities are the ones that talk to each other the most close-knit communities. So coming to a meeting like this, talking to each other, talking to your family, talking to your workmates, and talking to your politicians and business leaders, I think, is one of the most important things any of us can do, just to make sure we all understand the problem and the urgency. And adaptation plans around, loss of infrastructure, damage to infrastructure, food security, all the rest of it, really needs to be factored in at all levels of government. And just to finish off, just to reiterate, those curves that diverge, we do have a lot of power. If we, New Zealand, global community, choose to act, and we know how to reduce emissions of greenhouse gases significantly already, then we can make the future much more livable than if we don't do anything. So that's my little message of hope. I don't think we're all going to disappear in the next 10 years or even the next 50 years. But if we want a future that's as pleasant as it can be for future generations, I would say we need to get on with reducing emissions as soon as we possibly can. And there's a nice Canterbury sky to finish off with. Thanks very much for listening.